notes on anything on your notebook paper, anything about things you might need to know or you've missed. But I would really like to make a folder and give y'all these back as we prepare later at some point. But I'm going to have to get that done. All right, let's look at, which part are y'all looking at first? Calculator, non-calculator? Does it matter? Calculator portion. All right, calculator portion, which is the stapled portion. Any questions about the front page? Sandwich theorem? Most of you lost points. Most of you got the limit there because you could use your calculator, but you lost the sandwich theorem portion. So let's just look quickly at the sandwich theorem. So we had the limit as x approaches 0 of negative x squared cosine 1 over x plus 5. And you had to tell what it equaled, and if you graphed that, then you had to, bless you, you sketched a graph, and it was a funky looking graph. It looked like a parabola, but we don't care. I don't care. That kind of like smushed out at the top at 5. It was odd. And so it was easy to find the limit here, and this was 6 points. So I gave you 3 points for this, and then 3 points for showing the sandwich theorem, because it said to use the sandwich theorem to prove your answer. Some of you tried to prove it other ways, but since it specifically asked for the sandwich theorem, you needed to do that sandwich theorem, which the new book calls it the squeeze theorem. Same thing, sandwich theorem, squeeze theorem. Squeeze it between two values. So the first thing I take is something that I know, which is the cosine of 1 over x. It's always going to oscillate between what and what? Negative 1 and 1. Every single time it's going to go between negative 1 and 1, because regardless if you divide that, if you reciprocate the value for cosine, the cosine function itself is never going to go there between. Yeah. Take the trig function, because you're generally doing this on. Take the portion of the trig function, and since this is calculator, you could even graph this on your calculator and look at what it fluctuates between, and it's still between negative 1 and 1. Right. Or the range is another way to look at that. What's the range of that? Well, so now I need to go through and make the middle look like this. So to do that, I need to multiply by negative x squared everywhere, right? This middle. So I'm missing a negative x squared, right? So negative x squared, and of course here I'm multiplying by a negative. All my signs are going to flip. It's really not going to matter, but I'll flip them anyway. You multiply an inequality by a negative, it flips that sign around. And now I need to add 5, add 5, add 5, add 5. And the whole point in this is because my ends become something that I can evaluate the limit of very easily. In other words, what's the limit as x approaches 0 of x squared plus 5? 5, because if I can plug in a 0. And on this end, what's the limit as x approaches 0 of negative x squared plus 5? It's 5. So therefore, by the sandwich theorem, sandwiched between two values, the limit as x approaches 0 of f of x has got to be 5 also. If the two ends are the same, exactly, then the middle has to be the same also. That was probably the most missed on the test.
Can I ask you a question?
You can, Van. Calculator part? You jumped onto the non-calculator. All right, let's finish this one. That's okay. That's all right. Okay, so you take the trig function that's there, and I know that that trig function is always going to alternate between -1 and 1. All right, how about any more on the front of the calculator portion here, 1 through 3? Any more there? Is everybody okay? Number 2.
Wait, for number 2, how do we get the horizontal asymptote in? I just looked at the graph. Yes.
Okay, so what you essentially did on number 2 is you were defining the horizontal asymptote. So it said, and remember, this is a calculator problem, so definitely let that guide you. Over -2x6. And so part A said, what's the limit as x approaches infinity of f of x? So, right, I would get -2 here. And that, I could just graph it and look at the graph on my calculator, right? As I go way far to the right, what happens? And y'all need me to graph it and show you? It does look a little funky. Let me just graph it quickly. I don't have mine. I'm not going to hook my .cam and stuff up. So I can put my calculator up here and show you. I'm going to just do it this way. I have to find absolute value. Oh, absolute value of what? Is that what y'all's look like? No. But I think I put the wrong. Where's the negative sign on here? What? But I don't think. Oh, ha! There's another piece. Just kidding. My thing was covering it. Okay. If you had a standard 10 by 10 window, you would definitely see it. So as I go to the right, far, far, far to the right, and if you hit second graph and go into that table and just enter really big numbers, 100, 1,000, 2,000, 10,000, whatever, you'll see that that value gets closer and closer to -2. Right? The y value here is approaching -2. And then if I look, the part B says as I approach negative infinity, so same thing, I just went in my table whenever I did this and I changed all those values in my table to negative 100, -1,000, -10,000 to see what it approaches, and it approached +2 there. So part B would be +2. And then what happens is, because the limit as x approaches negative infinity of f of x is 2, then all it did was say identify the horizontal asymptotes. Well, by definition, if you take the limit as you approach either positive or negative infinity and you get a constant value, that is by definition a horizontal asymptote. So the answers from A and B were the answer for C. So I did 2 points apiece on those. For A, for B, and for C. So many of you got A and B right, but then you didn't get C right. Something there?
And so you showed off 1 point, you only got one. Yeah.
2. Oh, yeah. Any other questions? Questions about?
Is that how you found it? Well, I found -2 that I did before and divided by -2 because a horizontal asymptote is taking the first degree.
You did it based on a polynomial, but the top's not a polynomial. Well, I mean, it could be considered, yeah. But
that's right.
Then you miss out on the negative value of it because of the absolute value.
Because I did 4 divided by -2.
Right, but you miss out on the negative part of the absolute value. Because remember, whenever it's absolute value, you set it to the positive and negative. So that's why it didn't work. Yeah. 3, you said? So number 3 said identify, algebraically find and name the vertical asymptotes. So you have f of x equals x minus minus 1 over x squared plus 2x minus 8. And so I do need to factor that just to make sure there's no holes, that it doesn't cancel here. So I'm going to do x plus 4 and x minus 2. Nothing cancels here. And so I get negative 4 and 2. If I needed to prove that algebraic, if I need to prove that with limits, I would say that the limit as x approaches negative 4, and I should see that that goes to either positive or negative infinity. I'm not sure. But it didn't ask me to do all that. It just asked me to find them algebraically, which there you go. That's all you had to do. Oh, part B does ask you. Part B asks you for the limit. Using limits, describe the behavior of f of x to the left and right of each vertical asymptote. So each one's going to have two parts. It's going to have the limit as you approach from the right and the limit as you approach from the left. So you'd have the limit as x approaches negative 4 from the left, and then you'd have the limit as x approaches negative 4 from the right. And you would need to graph this to see. What do we have here? X minus 1. X squared plus 2x. Let's see. So as I approach negative 4 from the left, I'm going to negative infinity. Negative 4 from the right, I'm going positive infinity. 2 from the left, I'm going negative infinity. This number, part B, yeah, number 3. And as I go from the right, it's positive infinity. So it will look in limit notation. And then you'd also have to do 2 from the left and 2 from the right. From the left is negative, from the right is positive. Does it make dollars, man? You get it? Do you get it? Cents? It makes sense, but does it make dollars? Okay. Yes. All right, so number 4 asked us to prove that the in-behavior model was a good in-behavior model. So you had to, 1, identify it, but 2, you had to prove it. So I have y equals 3x squared minus, most of you got the in-behavior model, but it was the proving it that was hard. Couldn't? So, and I'll tell you for part B, 3x squared or 7 to the negative x would both be good in-behavior models for it. So either one would work there. You just get bogged down in the algebra of it as you find the limits is what happened with most of it. So for part A, if I did a left in-behavior model, right? So I want the limit as x approaches negative infinity, because that's the left end, right? As x approaches negative infinity, what is the graph doing? And so, this what? What? Well, I need this to go to 1. What do I need to divide? I divide what by what? That's right. I do the function. I need the limit function divided by, this time it was the left in behavior model. I need this to equal 1. And if I can show that, then I can show that it's a good in behavior model. Does that make sense? Okay. Because they have to be the same. And if you're the same on the top and the bottom, well, then that's 1.
You can put whole function over 3x squared.
So 3, well, I'm going to do the 3x squared, yeah. So when I worked this, I broke this into 3 different fractions. And when you break this into 3 fractions, it becomes a little easier to see what happens. This is 1, right? Infinity over infinity doesn't matter. I've got infinity squared and I've got an infinity on the top. 0. Really, really a lot bigger on the bottom, right? This is getting bigger way faster on the bottom. I'm going to call this 0. Well, yeah, because I'm going to negative infinity. So here I'm getting really, really big, right? But here I'm getting even bigger faster because I'm squaring it. If you have big over big squared, right? This is going to get bigger way faster. So I'm going to go to 0. It's not as big as the bottom. The bottom is getting is bigger exponentially faster. Right. No matter how big the number gets, if you had 1,000, what happens if you square 1,000? Huge, right? What if you have 1,000,000 up top and then you square 1,000,000 on the bottom? The difference is getting bigger between the numbers as you get bigger because it's a squared there. And here, because of that negative exponent, I come down, and so definitely way bigger in the bottom. Again, you have your calculator for this. If this piece confused you a bit, you could even graph these two, and let me show you, because you definitely want to use your calculator if you have it and you can. If I do 7 to the negative x, not that one, 7 raised to the negative x, divided by, what was it, 3x squared? Look at the graph as I go to, yeah. That's not what? Parentheses, yes. All right, same process for the write-in behavior model, and it does almost the exact same thing. Y'all need me to go through that? Y'all okay? Okay. Number 5 was average rate of change over the interval -2 to 1.
Was it 1 minus 0 minus 0?
Average rate of change was just the slope. The biggest problem there, you had -2 to 1. You had f of x equals 2x cubed minus 5x plus 3. Some of I don't know what happened here, but a lot of people miss points on this one. This is the interval that I'm looking at, right? Those are my x values. So that means I need f of -2 and I need f of 1. If you plug in -2, you get, where's my work here, -3. And if you plug in 1, you get 0. So all I'm doing is find the slope between the points -2, -3, and 1, 0. You weren't the only one. So slope came out to be 1 here. Yeah. You can. Yeah. Yeah. Seven minus x.
Like that. And then it's like 3x squared over 7 minus x. So it's like infinity, right?
Yes, because it's, well.
Because the 7x would go on top.
Mm-hmm.
So that would be infinity. And then 5x times 7x. Or minus. So maybe.
Okay, so those would cancel and you with the 1. Yeah. -3 minus 0 over -2 minus 1. Other questions about that one? Sorry, I know I'm running through. Yeah. Otherwise, your calculator takes order of operations over, and it thinks that you are saying -1 times 2 squared. And so, kind of, yeah. So it takes over order of operations, say square this first and then do the negative of it. So you got to put it in parentheses. Yeah. Sorry. Number 6, asked for the speed of the rock at t equals 4, which was, of course, an iRock problem. And so you had your equation of, I wasn't planning on going through every one of these, y'all. Do y'all need this one? No? Okay, good. 254.4 inches per second. I didn't take points off if you didn't put the units, but I did put a note that said, please include units next time, because that will be something they take points off if you don't include. How about 7? I think everybody got 7. Everybody get okay there? That was just slope there. Hang all the points. Oh, just be careful. All right, non-calculator. Front page, questions. No, that's okay. Yep. Number 5. Oh, the A-Rock. You good? No. Ooh. Listen, let me just tell you. Everybody's good on the calculator portion. How about non-calculator 1 through 5? Well, everybody is 4, and y'all are gonna kick yourself when you see what y'all did on number 4. I wanted to come through. All right, let's run through each one. Look at the picture. I'm not going to try to draw the picture up here, but it says consider the function given below. Which of the following is/are true about g of x? Be very careful. Make sure you read these kind of questions very carefully, because these are, by the way, these multiple choice type questions come from Barron's or old AP exams. Yeah. All right, so number 1 says the line x equals 1/2 is a vertical asymptote. And we can clearly see that, right? But be very careful. Look at the window that this is going to. This is from -3 to 3 by -2 to 2. That means your x's go from -3 to 3 and your y's go from -2 to 2. So every dash mark on that graph is 1 unit. Be careful about that. Now, the limit, so everybody's good with eliminating option number 1, yes? All right, option number 2, the limit as x goes to -1 of g of x is 1/2. The limit as x goes to -1 is 1/2. This is the one everybody missed. The limit as x goes to -1 of g of x. So on this graph, I said I wasn't going to draw it, but I am. 1, 2, ... And then I've got all this funky stuff over here I'm not going to worry about. -1, where does -1 happen? No, that's what you all looked at it and assumed that asymptote was at -1. But what's your window go from? -3 to 3, so this is -1, this is -2, this is -1/2. So the limit as x goes to -1 is actually this point right here, which is 1/2. So that is true. It was kind of misleading. Yes, it was kind of misleading. But beware of that kind of stuff. That's what, I don't know why they want to trick you like that, but be very cautious of that.
I literally wrote all of them out. I was like, there's no way.
I know. Number 3, everybody could see, I think, that -1 was an asymptote there. But there wasn't an option that said 3 only, because 4, the limit as x goes to infinity is equal to the limit as x goes to -infinity. You could clearly see that the ends of those graphs on the right and the left side were going to different values. So we eliminated 4. I think almost everybody crossed out 1 and 4, and then you crossed out 2, which left you with 3, and there wasn't an option for 3 only.
Yeah, I think it's.
You didn't?
Yeah.
So if you look, let me just put the other half of this. There we go. So this end, the left end is going to 0, but the right end is going to -1. So they're not the same. What was your question, Noah? I'm sorry. No, Noah, that's not your question. The right side of the graph.
So you're looking at where it's going this one, right? That's -1, but on this side, you're looking at that one.
Correct. That's correct.
I thought they were going to positive.
Okay, so when you go to positive infinity or negative infinity, those are vertical axes, is what you're looking at. But if you're going to, anytime you see x going to positive infinity, you're looking at the end behavior. Yeah. It could be a value and it could be an infinity or whatever, but you're looking at the ends of the graph. Is what you're looking at. End behavior, essentially, is what that is. All right, other questions about the first page, huh? I don't know who that is. Yeah. Okay, so you can have an asymptote that bounds up. Is that what you're talking about? Because it crosses right here. You can have an asymptote that bounds a portion of the graph but doesn't bound the whole graph. This asymptote is bounding this end right here.
Yeah, that is kind of.
It is. But remember the definition of a horizontal asymptote that we learned. If the limit as x approaches either positive or negative infinity of this function equals some value, it's a horizontal asymptote. And this does. It approaches a value on that end. So it's a horizontal asymptote by definition. Doesn't matter that it crosses over another part of the graph. If it bounds the end of the graph, it's a horizontal asymptote. How about number 5?
So we noted there's a whole.
Y'all forgot the name. A lot of people forgot the name. When you factored the top and the bottom, x minus 3 canceled, so you had a hole at 3. A hole is a removable discontinuity because you could plug it to remove from the graph. The x minus 4, or x equals 4, because x minus 4 equals 0, the 4 is a vertical asymptote, which is an infinite discontinuity.
You plug in the number.
So if I plug the hole on that one, right, the hole occurs at 3, right? So you got x squared minus 2x minus 3 over, and you didn't have to do this for this one, but that's right, you would, right, exactly. So 3 is my hole, so then if I plugged in 3 plus 1 over 3 minus 4, my hole would plug at, oops, -4. So if I define this as a piecewise, I would do, yeah, I saw you right plug the hole in that one. We'll do that one though, because a lot of you missed that one. Other questions about the front page? Flip over to the back page. The entire back page. All right, so 6, so they were 3 each on number 6, A, B, and C. And if you got A wrong, I didn't hold that against you on B or C, because that's the way they'll do on the exam. Just because you miss one portion, if you do part A wrong and you need part A to do part B, they're going to look at the answer you got for A and say, well, if I used that wrong value, would they have still done this correctly? And so that's what I did for you guys on this one. So if you calculated part A wrong, but you knew what to do on B and C, I still gave you credit there, if that makes sense. They will do that. They will. And there are a lot of times that you make it on there and you're working through an FRQ and you go, oh my gosh, I cannot do part B. I don't know how to do part B. Don't skip the whole rest of the problem. Write something and go to part C and try to do that, because sometimes they depend on each other and sometimes they don't.
Like the chemistry, if you put a wrong value, like 12.2, you're actually
Right, right.
tomorrow.
I don't know that they've released the date yet. I'm sure they have. I'll have to look. It's May. It's May. You should have. Yeah, you should have. If they've reformatted it, and I have to play around with it and see, because I like doing the little practice in there, but that's up to, if you would like to, you can. They're really helpful. There'll be a couple things we get to where I'll assign you a couple of them, but if you want to, for sure, and they're divided out by topic, and they do a really good job. I like them. Some I like better than others, but all right. Limits are a struggle, and limits don't go away, but we will also practice limits whenever we get into barons, as we'll do a whole unit on limits again. All right, here we go. Find the slope of the curve at that point. So I'm looking at IROC. Yes. If you're finding the slope of the curve, right, at a specific point, at a specific value, then I am IROCing it. Okay. All right, so I have the limit as h goes to 0, unless you use the alternate formula, which is fine too. F of x plus h minus f of x over h. I came over here and said, well, f of x plus h is squared. Oops, this is 4, sorry. What am I doing? F of 4 plus h is 4 plus h squared minus 4. Only my x gets the plus h. So no, he kept it. I don't know why. And so I get 16 minus 4, which is 12 here. So I'm going to plug in the limit as h goes to 0 of h squared minus 8h plus 12. Minus 12 over h. Gone, 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 gone. I end up with, is it minus? No, it should not be minus. It's plus. I didn't do the, I was like, what?
But it's not half of 12. I thought that you get 16 minus 8h plus h squared minus 4 over h.
Minus 4, but then you forgot, well, the 16 and the minus 4 there give you the 12. F of 4 is minus 12.
Yeah.
Y'all good?
The second half. I forgot the second half.
You about to what? Okay.
Oh, yeah, listen to this.
That does not. Just quickly here, tan line using that same slope. And then the normal line is the same thing, but the opposite reciprocal here. So we were given that point in the beginning, so there's where you use it, right? Hey, Rock, because you had a point. Really, what it was part of the work was done for you because they plugged in the for you.
It's not real slick. It just comes out form. It wouldn't have been the right way, but.
Yeah. Well, you wouldn't do no. You couldn't. All right, 7 we talked about before. Did y'all have any questions about 7? We talked about that briefly in class. If you want the limit to exist, that means the limit has to be the same from both directions. And if you want the point defined at 1, that was the first thing I did. If f of 3 is 1, I just went ahead and put that point on there. But then it said f is not continuous at 3. So for some reason, I need something to happen here that causes my graph not, even though the limit's the same from both directions. So yeah, you can do any kind of graph. You could do a line. It doesn't matter. Or, I mean, it could look like this. It could be a jump discontinuity. Oh, that is right. That is right. You're right. Yeah. Look at me. That's right. That's right. That's right. All right, for the last one, let me do the last one, then I'll give you a little break before we jump into the other stuff. What? We'll talk about this on the break because I got some stuff to take. All right, so this said find the value of m that makes the function continuous at the point x equals 3. 3 is my point where it's in question if it's going to be continuous or not. So I have to think about what makes a function continuous, right? And we know that the definition of continuity says the limit as I approach that value from the left must equal the value as I approach that must equal the value as I approach that value from the right, and it also must equal the function value itself at that point. Okay?
For a second, when I looked at this, I thought that a bunch of the answers were -3 in reality.
So if I plug 3 into each of those, right? The limit from the left would be m times 3 plus 4. The limit from the right would be 3 squared minus 11, and I need those to equal. It is so easy. Plug that in for, you want it to be continuous, and you want the limits to be the same from both sides. Because that is the definition of continuity. I did it. Which other one did y'all say you had questions about? 23.
Hold on, let me look at
The graphs in figure 3.1a show the number of rabbits and foxes in a small Arctic population. They are plotted as functions of time for 200 days. Okay. The number of rabbits increases at first as the rabbits reproduce, but the foxes prey on the rabbits. This is a morbid problem. And as the number of foxes increases, the rabbit population levels off. Is this not y'all's number 23? Okay, let me get the new book.
I ain't gonna lie, you were just telling us a weird story.
I have some book. What page are we on? Okay, lynxes and hares. In some northern parts of its range, the snowshoe hare is known to have a population that varies dramatically over time. The variation is cyclic? I don't know. Somebody help me. I don't know. And is tied to the population cycle of the Canada lynx, which preys almost exclusively on snow. Again with the morbid stuff. A simplified version of the predator-prey population model is shown in Figure 2.10. Figure 2.10a shows populations of hares in blue and lynxes in red, varying over a 9-year period in the 1800s. And then graph B shows the graph of the derivative of the hare population determined by the slopes of the blue curve in Figure 2.1a. What is the derivative of the hare population when the number of hares is the largest? Okay, well, this is just look at the graph. When is the number of hares the largest? At 2. So what's the derivative at 2? 0.
Because it's,
Go ahead, Noah.
what does 0 mean? Up?
It's leveling out. The derivative is because the slope at any maxes or mins, because that's when the slope becomes horizontal. So in fact, whenever it's the smallest, I don't even have to look at the graph, because if it's the smallest, it's again the derivative is 0, because at every max and every min, the derivative would be 0. Yay! Okay. Yes, it would both be 0.
Bro, I'm just glad it gave us that graph because we had to do that on our own.
When we're going to talk some more about derivative graphs, and we're going to do a little Desmos with it to help us match the graphs. Okay, what's the size of the hare population when the population of hares is the largest? What is the, what? Wait, what? What is the size of the hare population in Figure 2.10? A or B? I don't know. Let's go with A. When the population of hares is largest. So in other words, what's the most number of hares we have? 120,000. The smallest number of hares we have, 60,000. I have it. Do you need it? And then part C, what's part C say? Read it to me, man. Read it to me. Yes, you are.
Wait, so what was the answer to B? I don't remember us talking about B.
120,000 and 60,000. Approximately how many years left? Y'all just didn't want to do that because it was a word problem.
I just didn't know that.
I'm not gonna lie, I didn't.
It's okay.
Wait, how come you don't have a B?
I do. I'm just not welcome back here to shit.
You could have asked me to get out. I was on good.
I normally have 2 books, and I keep one up front and one in the back.
Ooh. Got 2 of them.
With new book, I only have 1.
You need to make it up.
Yeah, okay. All right, other questions? The graph of 27. Okay. I left you for number C on 23 on your own. Graphing f from the derivative of f, so sketch the graph of a continuous function, and it tells you that f of 0 needs to equal -1, so I hope we can at least all plot. Here. So what does the derivative tell us? Come on, I know, nothing. There's like... It tells us the slope of the tan line, and if the slope is constant, then what am I looking at? It starts with an L. It's with a 9, a line, linear, exactly. So this tells me that I'm looking at the graph of a line with a slope of 1 anytime x is less than negative 1. Here's negative 1, right? But I know that it's got to go through the point. One of the two of them has to go through the point 0, negative 1. So what does this look like?
So we just get a graph it?
A slope of 1 when x is smaller than negative 1. Smaller than negative 1. So a slope of 1 smaller but exclusive. I'm just going to start it here. It doesn't have to start here, but down 1 over 1, something like that. And then negative 2. Oh, I'm going to have to move it. Because it's got to be a slope of negative 2 when x is bigger than negative 1. Ooh, and it's got to be continuous.
Make sure you stand by people.
Leah, there's steps up here.
And you should patch it. And I'm busy for using your patch
No,
mouse.
I hit it on my computer.
The patch mouse.
I'll do this, Leah.
But I'm going to need to bring this over. It's going to have to be a part of this one. Right? So if this is yeah, so let me start with that point. What did it say, negative 1 or negative 1? I start here, and I'm going to let this one be the one, since this is bigger than negative 1, I'm going to let this be the slope with negative 2. So down 1, 2, and over 1. Right? 1, 2, over 1. Like that. Okay, is that a slope of negative 2 when x is bigger than negative 1?
Nah, because like it can be bigger than it. Yes. Yeah, I can agree with that. So it's a negative 2 physical.
And then the other one is a slope of positive 1 when x is smaller than. So this is going to be a slope of positive 1 from here. So down 1 over 1, it's going to look something like that. And I'm going to say that I'm going to say one of these is going to have to be inclusive because it said it had to be continuous. Oh, well, the function's not defined there, so I can still include it there, so yeah. It is continuous because I can draw it without lifting my pencil. No, this is f of x. This is the derivative. All right, so this gave you this. Remember, you have to remember derivative is slope, derivative is slope, derivative is slope. So here, this is the slope. So the slope is constant, which means I'm looking at a linear function.
Where is the slope, the derivative on that line? It's the red, right? No way.
Everything. So this is what, if I asked you, Noah, what is the derivative of f at negative 1? Or at negative 2. Let's go negative 2. So when x is negative 2 on this graph, 1, 2, what's the slope of that line? Looks like it's 1, right? That's what this is telling me. When x is smaller than negative 1, draw me a graph that always has a slope of 1. When x is bigger than negative 1, draw me a graph that always has a slope of negative 2. So this one's negative 2 when x is bigger than negative 1, and this one's positive 1 when x is smaller than negative 1, because there's your cutoff, negative 1. once you finish that, I'm going to let you work on your homework a little more. I'll answer a couple questions if you have them tomorrow as you finish that up. But I do want to talk about differentiability for just a minute. Yeah. I don't hold y'all really strict to stuff, but I do keep going. So if you get behind, it just puts you behind. I'm working on it during 4 o'clock.
Unless you have a class 4 o'clock.
Unless you have a, yeah, I'm sorry. On what? Will you put a pin in that and let me go over it tomorrow whenever everybody's done that? And I'll go over those two and then the questions from tonight. If you don't mind, that would be great. Unless we have time at the end. I understand. Put a pin in it, though, because we'll go over it first thing in the morning. We'll get started right at the bell tomorrow. Yeah. What class did you have? She let James miss the whole class on Friday to finish the test. So I don't. Well, I emailed her and I said, is it okay if he stays to work on his test? And she said yes. So if she's okay with that with you, I am A-okay with that. If my door is open, then my door is open. You may come in. All right. And my door's always open. I don't ever shut it because if I have something to do, I usually go somewhere else and do it. So y'all can still use the classroom. All right. Just quickly, I want to talk about differentiability because we talked about it a little bit, but I feel like I didn't define it very well, and I feel like we need to talk about a little bit more what makes a function differentiable. What do I mean differentiable? Oh my gosh, it sounds horrible, doesn't it? I'm going to put this in layman's terms. But I need layman's terms a lot. Layman's? You've never heard putting it in layman's terms? Breaking it down into easy. Differentiability is basically telling you if the function has a derivative at that point or if you can take the derivative at that point. So in order to know, I'm going to tell you when you can't take the derivative, and by telling you when you can't take the derivative, if you can eliminate those scenarios, then you can say, well, yes, my function is differentiable at these points. So when can I not take the derivative? Where is the derivative not defined? In other words, where does it not exist? I.e., not. We talked about one way already. Close. Okay, so the limits don't equal each other, so go a little bit further, not just when the one-sided derivatives don't equal each other. So in other words, remember, and I'm hesitant to say limits because if I have something like this, the limit at this point exists, right? And it's the same as I come in because I'm inclusive. I'm approaching this point here, right? So my limit exists, my one-sided limits are the same, but my one-sided derivatives are not the same. Do you see why? Because they're different slopes. This slope and this slope are not the same. So one-sided derivatives are not equal, even though one-sided limits are. I want you to see the difference there, okay? The derivatives are not the same from each side, but the limits are the same from each side. So I can have the limit defined, but not have a derivative. The function not be differentiable at that point. This is what we call, so I'm looking at, yeah. Did you say hold on for 1 second? Oh, I'm sorry. From the left and from the right. Hey. He's still looking at his homework. We're going to look at, shame, shoot. We're looking at 4 places where the derivative will fail to exist. This situation here is what we call a corner. Oh, this corner, yes. This is a place where one-sided derivatives are not the same. Derivatives do not equal. So the function is not differentiable at that point is the terminology we use. Yeah.
Even if the derivative limits were the same, what it would because like how can you like the derivative of it. Let's say like the derivative is the same. The normal graph. Right? So like let's say you know how we said like the two like even if the limit is the same from the left and right, the derivatives are not going to.
Not necessarily. It depends on the graph. They could.
Okay. Well, but what I'm saying is like the derivative doesn't look the same, right? So therefore, if the derivative looks the same, the original has to be different, right?
Yes. I think.
Understand like basically the opposite.
Are the same. So if we're on that graph, and that's the graph of, you could literally say, for this, you could literally say, because this is a corner point there, it is not differentiable. I mean, that is acceptable. You don't have to show both. And it probably did, and I hadn't defined it yet. Right. And the derivative here, so it'd be the slope of this line from the left and the slope of this line from the right. Yes, absolutely, because it's linear. So this mostly happens with your what kind of functions? What are you looking at? What is this the graph of? An absolute value. That's a great example of a corner function. So the function is differentiable on its whole domain with the exception, of that vertex point, that corner point. It's not differentiable. Even though it has a limit that exists, it's not differentiable at that point. Does that make sense? Okay. Number 2. Remember I told you there's 4. Number 2 is what? It's called a cusp. Okay, so this, you want to see what?
You're making a joke.
What? I don't get it.
This corner.
Okay, that's not nice. Formal definition here is where the slopes of the tan lines approach either positive or negative infinity as you look at a certain point. And this, when you see it, it makes sense. Just to try to define it doesn't make much sense. These are mostly our rational exponent functions, something like x to the 2/3. Remember, I'm talking about points where I am not differentiable. Okay? So this looks like this. It looks kind of the same, but it's kind of curved out. This slope is getting steeper and steeper and steeper. It's not a constant slope. And so even though if you did this, the slopes are approaching that same value of negative infinity, right? They're getting...
That one's getting bigger, but that one's getting smaller.
But they're still going to infinity, right?
Right.
But that's what we call a cusp. Do what? What is? Say that again? Well, so this side is going towards negative infinity, and this one's going towards positive infinity. The slope of they're going towards infinities. Mm-hmm. Yeah. at 0. What is f prime, if this is f of x, what is f prime of 0? Well, because 0 is the only point on this graph where it's undefined, this does not exist. Why? Because there's a cusp there. The one-sided, yes. You could do the one-sided derivative, but you couldn't do, yeah.
So I'm trying to understand what's the difference between, I know like the splits on both sides are different than from the absolute value, but like when you say cusp of the point, like what's the difference?
Like a cusp and a corner.
Yeah.
They're very similar. The corner are linear functions coming in together like that. The cusp is not linear. It's more curved like this as it comes in. But it's the same. Yes. Two others, and they're a little easier than these two. I started with the hardest two. Number 3 is going to be a vertical tangent. Okay, but it sounds worse than what it is. Let's think about the cubed root of x. Okay, as you graph the cubed root of x, if you really zoom in here, the way the graph kind of looks is more like this. There's this space here where it looks like it almost turns into a vertical line, and it almost does. That's what we call a vertical tangent. If you were to do the slope there, the slope of the tangent line there, you would get some value over 0, which is undefined, because there's no vertical change here as you go in there. Okay, it's easy to see graphically. This doesn't happen as much. The corner and cusp are the two most common, and the last one that we're going to do. Sorry, I know I'm going a little bit fast. The slope, yeah. The very last one is the one that probably would make the most sense to you. If a function is not continuous at a point, then it is not differentiable. And that is an important point to remember. In fact, I'm going to put that as in. If a function is not continuous at a point, thank you, Van. It looks like it's got a little angel halo on it. If a function is not continuous at a point, then it's not differentiable at that point. Holes, asymptotes, jump discontinuities, oscillating discontinuity, all of those discontinuity types that we learned, those are non-differentiable at those points. Let's see. Piecewise, a lot of times here, that'll be something like the one on your test that was like x minus 1, and once it was factored. I don't remember what it was. But whatever that function was there, I don't even know what that looks like graph, but there's a hole at 1, right? So there's a hole at 1, and then the graph goes on doing whatever it does. Here, this would be not differentiable at the hole itself, because it's not continuous at the hole.
So when you say you're not differentiable at this,
right. That's right, because you can have a function that is differentiable over its whole domain, but just not at certain points. So your homework tonight is really, really easy. Because this is an intro. It's looking at graphs and telling if it has any non-differentiable points on it. So you're looking for discontinuities, you're looking for corners, you're looking for cusps or vertical tangents is essentially what you're looking for. Right, that's exactly right. So you're looking for one of these four scenarios, and if one of those four scenarios does not exist, then it's differentiable on its entire domain. But you can have a function that's differentiable at all points except one, or except 2 points. So we're going to do page 121 through 16. Again, those are just looking at graphs or graphing them on your calculator and saying, yes, it's differentiable on its whole domain, or no, it's not differentiable at this point because there's a corner, or because there's a cusp.